Okay, good morning. Let's get rolling. Today what I want to do is look at some of the characteristics of the Bode magnitude plot. Remember that I said the Bode plot has basically two plots. One is magnitude versus frequency, and the other one is phase versus frequency. And today we're going to focus just on the Bode magnitude characteristics. We're going to use the computer to see how the computer generates it, and then we're going to try to superimpose on the computer plot what we would do by hand, what we call straight line approximations or asymptotic lines. We'll look at the phase characteristics in more detail at a future time. The command that we're going to use on the computer to generate the plots will do both the magnitude and phase simultaneously. So if you kind of want to peek ahead and look at the phase plots, we can do that as well. But I won't focus on that today. Now remember, if we're getting to that time of year where people are doing interviews and you got special events coming up, just remember that the lecture notes are being recorded, courtesy of Matt here, and put on YouTube. And so you can take a look at that. And things that I scribble on the document camera, I'll be happy to scan them and email them to you if you need them. Okay, so pass that word around. There really is no reason for anyone to be missing a set of notes. What we're going to use this morning is we're going to use in MATLAB a command called Bode. And I'm going to basically show you how to use the Bode command today. All right? And we're going to then study the different characteristics. And so the first thing we're going to do is let's take a look at, you're going to turn MATLAB on, log in, and then let's take a look at some very basic terms. Let's first do this one. Let's do some simple ones. Let's consider G1 of S is 2 over S plus 2. This is what I would call a first order. It's a transfer function, and it's got a single pole. It's first order. Okay. The second transfer function that we're going to take a look at is just the opposite of this, the inverse of this. Let's just call it 1 over G1 of S. So what we can do is let's go ahead and enter these into MATLAB. And in MATLAB, what I would do is I would say G1 is a transfer function. The numerator is 2, and then the denominator is S plus 2, like so. Okay. And then if you want to enter in G2 manually, you could just reverse these two terms. Reverse these two terms within the command. Or if you want to try this, 1 divided by G2. All right. Now, we're going to use the computer to go ahead and generate the Bode diagrams. And then I also want to, I've handed out this sheet of Bode plot paper. We're going to, semi-log paper, and we're going to kind of set it up and do it by hand as well, so you can kind of record what you saw on the screen on a piece of paper and try to remember the salient or important features of what you do by hand. So to generate the Bode diagram, just the diagram alone, if you don't want to save the data or anything like that, just use the Bode command. And what we would do is you would say Bode of G1, and then you would be done. It turns out that we can compare multiple Bode plots by just adding them on as additional models. So I can say do a Bode plot of G1 and G2 like so. Now the Bode plot is going to be generated. It's going to draw the diagrams, but it won't draw these grid lines. And it's kind of helpful to see the grid lines. And so I'm going to string another command on here and just call it grid on. Okay, there's a space on here. Just say grid on or grid, because the default is that the grid is off. So you say grid on. Okay. If you're just stepping in, you might want to come in and pick up a sheet of semi-log paper. Okay, so that's what we would do in MATLAB, what you're seeing up on the screen right there. Let's go ahead and let's take a look at how we would set up our semi-log paper. So we're going to hold our paper like this. Okay. Notice that the horizontal axis is on logarithmic scale. We see a compression right here. See how the lines are closer on the right-hand side, and they're kind of more spread out as you go this way. So they're more spread out. So things get compressed, 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 and then we start over another cycle. Get more and more compressed, start another cycle, and so forth. So this is a 4-cycle paper. What I'm going to do this morning is I'm going to go ahead and label the diagram here. I'm going to label, let's put maybe 0 right here. This is 10 to the 0. Find your major division and just kind of highlight it there. There's put a heavy tick mark. That's 10 to the 0. That's 1. And so this will be 10 to the 1. This will be 10. This will be 10 to the 2 at this tick mark. That will be 100. Okay? And you can continue on. This will be 1,000. Let's label our axes. This is frequency. The default is radians per second. And since we've already executed the Bode diagram, you may take a look and see how the computer labeled it. It should have labeled it in a similar fashion. I think they call it Bode radians per second. I mean frequency radians per second. Okay? It's going to show you 2 diagrams. It's going to show you magnitude plot on top and the magnitude on the bottom. So we're concentrating on the magnitude, so I'm going to put right here, you can put the word magnitude or gain. Magnitude. And the units are dB. And remember, dB means 20 times the log base 10 of our gain, or our magnitude. Okay, that's what this is, dB. In EMAG, as I said last time we met, this is 10 times the log, because they do with power, like how much power am I getting irradiated with by my microwave oven. Okay, so for the sake of discussion today, let's just put 0 right about here. And I'm going to put, let me put plus 20, plus 40, plus 60, like this. These are the units. So this is 20 dB, 40 dB, 60 dB. This is minus 20, minus 40. Okay. So let's take a look at this diagram now. You should be seeing several curves on the magnitude. You got an upper picture and a lower picture. The upper picture should be labeled magnitude, and the lower picture is labeled phase. We're going to ignore that for now. But on that picture, you see 2 curves. Do you see the 2 curves? Okay. I think maybe one is red and maybe one is blue. And to help us distinguish between the 2, let's add another command, another Bode command that says let's label our curves. Let's add a legend like we do on a map. And so you just use the legend command, L-E-G-E-N-D, legend, and that will produce a legend. But let's put the text in that we want to use on our legend. And so let's say for the first one, let's put in an apostrophe. We're going to put in text now. Let's call it G1. That closes it. And then comma G2. Because we've got 2 curves, we want to label each of the curves. And so let's put in some text like G1 and G2. And it's going to label the curves. Now, unfortunately, it's going to label them in the phase plot because it first produces the magnitude plot, and then it produces the phase plot, and then the next command is going to go into the most recent plot window, which is the phase plot. And so in the phase plot, it's going to label G1 and G2, but you can use that information to see which one is G1 and G2 in the magnitude plot. Okay? So you should see something like this. You should see 2 curves, and they start off initially flat like this. They start off flat down here. Okay? And then one of the curves goes up, correct? One goes up, and one goes down. And you should see it's going to look something like, I'm gonna go ahead and label, I'm going to sketch mine. One of them is going to go up like this. And the other is going to go down. Like this. And we should see in our minds that this is G1 and this one is G2. Oh, I'm sorry. I got it backwards. This one is G2 and this one is G1. Okay. This is the term that looks like 2 over S plus 2, and this one's the inverse. This is S plus 2 over 2. Okay. See a gradual curve that goes up like this, and then it just goes on forever. The other one's a gradual curve right here, and then it goes down forever. Okay. Have I said anything contradictory to what you're seeing on the screen? No? Good. I'm not losing my mind. All right, so we can't produce these very well by hand. Okay, the computer is generating a bunch of frequencies and then substituting S equal to J omega in and doing the calculation, calculating the magnitude, and generating the plot. What I'm going to show right now is how we basically produce the hand sketch. To produce the hand sketch, what we do is we need to find the frequency at which this pole occurs. Okay, this pole occurs at omega equal to 2. So you need to find on here omega equal to 2 on this frequency axis. And so I'm going to label it right here. This is 1, this is 10, here's 2. Put a little caret mark there. This is omega equal to 2. This is what we call the corner frequency. And my green pen is dying, so I apologize for that. We'll go back to maybe a black pen or maybe some other color. That's the corner frequency. So what we do is at the corner frequency, take your pencil or take your pen and make a little dot right here at 0 dB horizontally, vertically. Right here vertically at 0, come across, and right here at omega equal to 2, make a little dot right here. That's where the corner is going to exist. And so what you do is you draw a straight line. The hand sketch is a straight line that goes out to here, and then there's a straight line that follows this curve. Now I'm going to sketch this curve, and I'm going to draw with a particular slope. You have to draw it kind of accurately here. Here's omega equal to 2, right here, omega equal to 2. 0 dB. Let's find omega equal to 20. Omega equal to 20 is right here. Okay. Put that tick mark in. Now, at omega equal to 20, come down 20 dB, put another tick right here, like so, a little mark. And now you got a dot here and a dot here. You could go to omega equal to 200 right here. Here's 200. Come down 40 dB. Put a tick mark right there. Now you got 3 dots. So now draw a straight line through those 3 dots like so. All right. Give you a chance to draw. We're drawing by hand something that kind of mimics what you're seeing on the computer. Now on the computer, the scaling is going to be a little bit different. Okay, I think for this particular example, it probably won't draw 4 cycles of frequency. It'll probably just draw 3 cycles of frequency. And the scalings here might be a little different. They're going to pick some scalings that are convenient for the computer, but not for me or you to do by hand. Okay? So there are a couple features that I want you to see here. This is the first order pole here. This is a first order 0 here. These are first order factors. This is a pole. This is a 0. We see that with zeros, the magnitude increases with frequency. So that's one of the things that we want to note here. Let's make some notes. The magnitude increases with frequency. Okay, it increases with omega for the 0. The magnitude decreases with frequency for the pole. Okay, so that's what the first observation is as frequency increases, the magnitude of the zero increases, but the magnitude of the pole decreases. Okay. I introduced this concept of the corner frequency. So note the corner frequency. In our example, the pole is at s equal to 2, so omega equal to 2. So that's this number. Here's the corner frequency. Okay. The magnitude is basically flat up to the corner frequency. Up to the corner, it's basically flat. Now after that, above the corner, let's take a look at the slope. Let's take a look at the slope of this line. This slope is going to be, it changes 20 dB in 1 decade. Okay, so this distance from here to here is what we call a decade. This is 1 decade. This distance from here to here is also 1 decade. If I go from 0 to 10 to the 10 to the 0 to 10 to the 1, that's 1 decade. Anywhere along here, a factor of 10 is 1 decade. Decade means times 10. Okay, times 10. So above the corner frequency, the slope is either plus or minus 20 dB per decade. Okay. These are the notes for the first order case. So take a look at your computer screen and then try to mentally draw in some straight lines. You might want to pick up a piece of paper like so and put it on your screen and kind of lay it on there and say, yeah, that looks like 20 dB per decade. And yeah, that looks like it's flat. And yeah, I can kind of see where I would put a corner right here at omega equal to 2. So this slope is 20 dB per decade. It's a negative 20 dB per decade for the pole. This slope is a positive 20 dB per decade. So if I were to put a little thing here, this means slope. This is plus 20 dB per decade. Okay. Oh, I'm sorry. Gosh. Minus, thank you. Somebody said minus. Minus 20. This one is plus. Plus 20 dB per decade. You know, northern hemisphere, southern hemisphere, you know, things look upside down. Okay, no, bad joke. All right, that's a distance of a decade. Now, there is another unit of measure other than the decade. The decade means times 10. Okay. Now, there is another term called an octave. Okay. It's a different scaling, not times 10. It's octave. OCT, octave. What does that make? What number does that make you think of? 8. But it's not 8. Okay. So DEC, decade, makes me think of 10. Oct makes me think of 8, but it's not an octave. Okay, so now I'm about to expose my lack of musical understanding, but I'm going to try to delve into music a little bit. Anybody here play piano or took piano? 2, 3, not many others? Did not take piano? Your mother didn't make you do piano? Well, I can't sing worth a lick, and I have very poor musical skills, and so I said, when my kids were born, I said, they will not grow up with my handicap. We're going to make them take piano. So all 3 of them took piano. And it was wonderful. We had music in our house. Okay, so you piano guys, you know where, is it called middle C? Is in the middle of the piano? And then what's the next one up called? It's an octave. It's one octave away. Okay? It's the next C up. So then, do you know the difference in frequency between that middle C and the next one? Okay. I know that middle A is, I think, 440 hertz. 440, does that sound familiar? 440 is middle A. One octave above that is 880. Okay. So octave here does not mean times 8. It sort of means 8. How many white piano keys are there between that C and the next C up? I know a piano's got these black and white keys. You know, the black ones sound off and the white ones are okay. So there's 8 white piano keys, right? There are 8 keys between middle C and the next one up. 8 keys. But the frequency difference is not 8. Okay? So the frequency difference is times 2. Times 2 in frequency. This is 8 piano keys. But it's not 8 times in frequency. It's 8 free, you know, do, re, mi, something like that. Okay, so if we want to take a look at the slope, you can say it's 20 dB per decade. If I go up by a factor of 10 in frequency, this slope has dropped 20 dB. Or here, it's increased 20 dB. But sometimes I don't want to draw a line that long, a whole decade. I want to draw a shorter line. I want to say, what is the slope if I just go by a increase in frequency by a factor of 2. So here, say, for example, is omega equal to 2. An octave away would be omega equal to 4. So omega equal to 4 is right here. That's an octave. That's an octave. Okay. This distance from 100 to 200 is also 1 octave. It's a doubling in frequency. And so from 1 to 2 is an octave. And notice if I put my fingers here, that's an octave. This is also an octave. These are all octaves, a factor of 2. If you go from 4 to 8, 8 is right here. That's also an octave. Okay? So if I go away an octave, we want to know how much does it fall, or how much does it increase. Okay? The answer is, this is approximate. Let me come back. The slope is plus or minus 6 dB per octave. Okay? 20 dB per decade or 6 dB per octave. The 20 dB comes in from the idea that, remember when we looked at dB, dB is defined as 20 times the log of the gain. So if the gain were to increase by a factor of 10 because of the frequency change, then we're going to get a change of 20 dB. Okay? So this diagram here kind of summarizes the first order 0 and the first order pole. The main thing that we know is that zeros go up, poles go down. Okay, so that's one thing to take away with us. And then first order factors increase or decrease by a factor of 20 dB per octave or 6 dB per octave. Now, these are called asymptotic lines. Asymptotic lines because when you're away from the corner, the curve, the actual curve, and the straight line are really close. And the further away you go, the more they're correct. I mean, the more they match. The straight line is pretty correct. Here, the straight line is correct. Here, there's a little bit of error right at the corner. If you were to zoom in there, if you zoom in here, there's about a 3 dB error. Three dB difference between where the corner is and where the actual curve is. Let me zoom in a little bit on a blank sheet of paper. Let me suppose I say, let me just call this the corner error. So the corner looks like this. Down here, it's going minus 20 dB per decade. Here, the slope is flat, 0 dB per decade. And the actual curve is going to look something like this. It's going to get closer and closer as we get away from the corner. And here I'm going to get closer and closer as I get away from the corner. But right here at the corner, this error is 3 dB. So this looks like it's it's flat, but the curve is down 3 dB. Okay. This is the corner. So if you want to do an accurate sketch, sketch in the straight lines, come down 3 dB, put a little dot, and say the curve needs to pass through there. If you want to be, if you're obsessive compulsive and want to put in a few more dots, let's go away to 1 octave away from the corner. This is 2 times the corner. Let's come away 2 times the corner this way, 1/2 of the corner. This is 1/2 corner. 1/2 of the corner frequency. This is the corner frequency right here. And this is 2 times the corner frequency. Okay. Now, 1 octave away, this error here, there's a 1 dB error. Right here, there's a 1 dB error. So if you want to do, put in a few more dots, come down 1 corner away, or 1 octave away from the corner, put a little dot, 1 dB down. Same thing here. The further away you get from the corner, the smaller the error is. Okay. And then so just kind of draw a curve through your something like that. All right, these are just little tidbits that are probably increasingly not important in real life because we do things by computer like so. Okay, these are our 2 functions, and we studied them. All right, we have another piece of paper down here at the bottom. It's blank. We're going to take a look now at the second order terms, second order factor. Let's generate several transfer functions. Now, the second order transfer function, the standard form, let's do a standard form. Okay. We're going to do a second order model, and the second order model, it looks like this. Remember, in the numerator, well, it's when we were studying the time response, there was gain k. In the numerator is omega n squared, and in the bottom is s squared plus 2 zeta omega n s plus omega n squared. Okay. For the sake of discussion this morning, we're going to just let k be equal to 1. And let's pick a number for omega n. Okay, so let's do this. Let's first of all say clear all. Clear all in MATLAB. Okay, wipes our workspace clean. And I want to plot several transfer functions. And so, but the thing that's going to be constant in all of them is this undamped natural frequency. So let's define an undamped natural frequency. Let's say omega n equal to 4. Okay. So let's do several models. Let's do zeta equal to 1, zeta equal to 0.707, zeta equal to 0.5, zeta equal to 0.2, zeta equal to 0.01. Okay, so this will be the first zeta, the second zeta, the third case, the fourth case, and the fifth case. So let's build this transfer function. The first transfer function I'm going to call it G1. It's a transfer function. The numerator is omega n squared, but I've already entered in omega n. So I'll just say omega n, you can just type in as, let's call it Wn, because you don't have Greek letters on your keyboard. Call it Wn. Okay. So we want omega n squared, so put a caret mark. There's that. Okay, that does this part. And in the bottom, we want s squared. The coefficient is 1. And then we have 2 zeta omega n. So let's just go ahead and say 2 times zeta. So we'll say 2 times zeta 1. Put the 1 there. And then we'll put in the omega n, Wn, like this. That takes care of this factor. And then the third factor is omega n squared. The third coefficient, I'm sorry. First coefficient of s squared, this is the coefficient on s, and this is the constant coefficient. We'll do that. It's a lot of typing just to generate that first model. But the next few models are going to be easy. Just hit the up arrow on your keyboard, and G1, in this last command, pops up. Okay? And then go ahead and modify the commands. Just change this number to a 2. So now you have, turn this into a 2. And don't change this. Don't change this. Don't change anything, but change this number. Change it to 0.707. After you change this and this, just hit the return button, and it should pop back up, and it should give you G2. G2 is just changing this. Okay, so this will be G2. This makes G2. And then I hit the up arrow again, and the command for G2 should come back. Modify it and call this a 3. And then use your cursor, use your arrows and find it and turn this one to 0.5 and so forth. Do you have a question? Do you have a question? Okay. I'll give you a few minutes and put in 5 models. You can type out longhand this way if you're a good typist. I'm not. I like to do it first time, stare at it, make sure I got it right. And then just go ahead and modify G1 several times, or each of the last commands several times, so that you produce different models where zeta, the damping factor, is changing. We're going to leave omega n constant in all of these. I'll give you a few seconds to put that in. If you've got that in, then what I'm going to do is let's also label our frequency axis on a clean sheet. We had the first order case up here. Let's take a look at the second order case. Let's label again our frequency axes. This will be 1, 10, 100. Label this as frequency. Units are radians per second. Label this axis again. Call it magnitude or gain. Units are in dB. And we're going to put 0 right here on my graph like this. And we're going to use similar scales as I did earlier. I'm going to call this 20, call this 40, call this 60. Minus 20, minus 40, minus 60. Okay, so I'm going to sketch the hand sketch. Okay. The corner frequency in this case here is at omega n. And so omega n equal to 4. So I need to find 4 on this scale here. Okay, remember, this is where people, 10% of the class will make an error because they're not practiced reading log scale. Okay, 10% of you will get this wrong. At least that's been the past history. Make sure you find omega n equal to 4 correctly. Should be right here. Okay. At omega n equal to 4, go to 0 dB, put in a dot. This is my corner frequency. These models we are constructing are second order, but they're poles. And so the straight line approximation is going to be flat up to here. And then the slope will change. Okay. What will the slope be? Well, let's look at our previous first order case. With the first order case, the slope was a factor of 20 dB per decade. This being second order, we think the slope will be 40 dB per decade, right? So what we want to do is we want to come down 40 dB after I go a decade. So a decade above 4 is 40. So here's 10, 20, 30, 40. Here's 40. Come down 40 dB and put another dot right here. Come down 40 dB below where I was. Here's 0 dB. Come down 40 dB. Okay. If I want to put in yet another dot, let's go another decade up. So that'll be 400. So it's 100, 200, 300, 400. 400's right here. And I want to come down another 40 dB, so that'll be down, I'm going to be down at minus 80, so I should be right here. 1, 2, 3, 4, yeah, right here. Put a straight line through things. Okay. 10, 20, 30, 40, right here. Okay. This is the straight line approximation. This is a second order pole, single, second order pole. This slope is minus 40 dB per decade. What would it be? How many dB would it be per octave? Anybody want to guess? Let's look back at our first order case. In our first order case, the note said the slope was 20 dB per decade or 6 dB per octave for a first order case. For a second order case, this would be minus 12 dB for 1 octave. Okay. Now what you should be seeing on the computer screen is a series of curves. Okay. I'm sorry, we haven't executed the Bode plot yet. So let's do a Bode command. Let's come back to this screen. This is where we did all our different models. The only difference is zeta is changing in all of them. So we should have a total of 5 G's, G1, G2, G3, G4, G5. So let's do this. Let's do Bode, G1, G2, G3, G4, G5. It's going to do the Bode plot. It won't put on the grid lines. We like to see grid lines, so we'll say grid on. Okay. And to help us kind of distinguish who's what, well, you can type in a legend if you want. G1, G2, so forth. You got to fill in this. ... won't work on the computer. It only works in my mind. But what we should see is we should see one of the curves is going to look like this. Okay. This is for zeta equal to 1. The error here is going to be 6 dB. For zeta equal to 0.707, it's going to be a little higher, like so. That is the smallest damping factor we can get before this thing starts peaking up. For 0.5, let's see what do we have. 0.1, 0.707, 0.5, it should bulge up a little bit over this flat line and then fall back down. And then 0.2, the bulge is going to be even higher. Okay. And then 0.01, it's going to be really peaky like this. It's going to jump up like this. So you should see a sequence of, a series of curves, a family of curves. You'll find this in your textbook as well. These are the curves. This is the frequency response for a second order case. Okay. This type of behavior is what we call resonance. Okay. It's called resonance. This peak occurs at the resonant frequency. And as zeta gets small, this is decreasing zeta. As zeta gets small, the peak gets closer and closer to the number omega n equal to 4. Okay? Did I talk about before in a previous class about the problem of going up to a toll booth in your car and there's rumble strips on the ground? I didn't talk about that example. Okay. Let's see. When's our next vacation? Spring break. No, that's too far away. Fall break. We got 2 days off. Okay. Fall break is coming up sometime in October. You can take a quick run down to Florida because you're still young and you can drive all night. But there's a toll booth around Orlando. Okay, a series of toll booths because Florida has toll booths. So you're driving along the highway, you're coming up to this toll booth, and they're going to warn you that the toll booth is coming up. There's going to be all kinds of signs, toll's coming. And one of the things they do is, if you're going to pay by cash, you need to get over in the right-hand lane. They want you to slow down because they don't want you hitting the toll booth too quickly. And so what they'll do is they'll put bumps on the road. If you go over the bump at a very low speed, then the frequency at which those bumps appear is going to be a low frequency. And the car is going to go up and down with the bumps. That's a gain of 0 dB. Whatever the bump does, the car will do that also. So it's a 0 dB gain. Okay, the car body, here's the car body, goes up and down with the bumps. Okay, so if the bump goes this high, the car body is going to go up the same amount. Now, those of us who've been driving around toll booths a lot know that there's another way to get to the toll booth without having to deal with these annoying bumps, right? You can also do it here in Auburn. There's a couple places where we have those speed bumps, okay? Another thing you can do is you can drive really fast, okay? And you say, yeah, I know there's rumble strips on the ground. I can drive real fast. And what happens is I go over the strips real quickly, and what happens? I don't feel it in the car. I hear this, brrr. I hear it, brrr. Oh yeah, I went over the rumble strips. The car body doesn't respond. Okay? The wheels respond like this because they go over the bumps, but the car body, because there's a spring and a damper, the car body doesn't go up and down much. And you like that because you say it didn't bother me. You know, unlike when I'm driving at low speed, if I go over the bump, the car body goes up and the car body goes down, up and down. But if I go at a higher speed, those strips seem to appear at a higher frequency. And so the response of the car body decreases. And so you're out here at this gain, low gain. But there is a particular speed, a particularly bad speed, at somewhere here, depending on the conditions of your shock absorbers, where you can get the car to make it feel like it's going to go and jump up in the air. Okay? The response is very strong. That's the resonant frequency of your car. Okay? So go find some rumble strips this weekend and try it. Okay? Try going over the speed bumps at low speed. Confirm that the car body basically just follows the vertical motion of the car body, just follows that of the bump. Go over at high speed. Okay? Lakeview Baptist, where I go to church, there's a bunch of speed bumps. Go over those speed bumps. Okay? Do it in the afternoon when the kids aren't around. And then go over some of those speed bumps at just the right speed and see if you can get your car to launch into the air. This is resonance. Okay, okay, let me close because I'm about out of time. Let me ask you this quick question. What do you think would happen if I were to do these plots for a second order 0? What do you think the plots would look like? Okay? So try to take that idea away from us. We've got a lot packed into these 2 slides. Zeros, poles, slopes, all kinds of things. All right? Now, these are not all the factors that we need to deal with. They're the most common factors. There's a couple other factors that we'll have to deal with, but we will take a look at this on Friday. On Friday, let's go back to the regular classroom. We won't use the computer. We'll do things by hand. We're going to talk about how to sketch these things out by hand. Okay, put all these together. When we've got more complicated functions, how we can put them all together. Okay, that's it for today.